Yeah, now recording. Hopefully recording the right screen. Yeah. Okay, so yeah, next week, Dr. David McMeekin will be talking about localization, mapping, spatial stuff, which is really, really useful in many of our IoT applications, knowing where the device is, how it's moving, how it fits into the environment. So interesting little one there. Okay, so fourth of our semesters, welcome everyone. Again, note these will be recorded. Thank you, Savash, otherwise they wouldn't have been. And posted up to YouTube. You can watch them later if you like. So this week, just going through the requirements for next week, next 2 weeks, sorry. We're getting fairly close to the end now, so we should be nicely along. During this session, if you haven't received a reply to any emails, please let us know and we'll sort that out for you this morning. We have material due, the market research and costing plan. I'll talk a little bit about that today, due 30th of May, this coming Sunday. Okay, so basically we've covered all the fundamental stuff now, and it's time for your individual project development. Again, we're quite happy to talk to you individually via email, or we can arrange Skype calls if you want any help with something in particular. There's no real content for the next, or for weeks 9 through 12, but we'll still have these sort of discussions. This is the time we expect you guys to be in contact with us, asking any technical questions on the implementation, and maybe we can talk a bit about how we do our curtain projects as well for our honour students and master's students. Okay, congratulations, everyone's completed their videos, and Sebash has been through and marked them all. You should have results there. If you haven't, please let us know and we'll chase it up. Check for the feedback. I don't think we had any IP sensitive ones, did we, Sebash?
Yes, there was one that I marked individually.
Okay, so they would be best contacting us regarding any feedback.
Mhm.
All right, so this fortnight, again, use your team as a sounding board for how you're developing things. Again, don't forget the market research costing report is due on the 30th. And you should know or have a reasonable idea of who the best person for your project to help out as far as the advisors go is. Moving right along. So the market research and costing plan, just a reminder, it's 15% of your overall mark. Your industry analysis is 25%. And that's really looking at what the problem you're trying to solve is, why this device or solution needs to be developed, things along those lines. Competitor analysis is 10% of the overall mark. That's looking at any competitors that already exist and in the market and what advantages they have over other products or new products to market. Very much looking at how you can compete against these already established companies. The products and services, what you're actually offering is 30%. This is the bulk of the work on how your solution is actually adding value to a process. I saw an interesting thing actually on value add, non-value add, and business value add as a way of breaking down how you go around any of your processes. So value add is anything that adds to the process of getting from your point of order initialization through to delivery to customer. Your business value add is all of the items that you have to do as a business. So keeping accounts, receipts, dealing with orders, chasing up orders. These are things that don't add value to the product, but are necessary to actually conduct the business. Both of these, the value add, you need to do because that's what gets your product out there. The business value add you have to do, but should be kept to a minimum. And anything that is non-value add, and this is where you say, right, I need to do this for the business, or I need to do this for the product development and product delivery, but I'm doing all of these other things. That's the non-value add. And these are the things you should look at cutting out to try and get an efficient process. And by laying these tasks out in a timeline, you end up with lots of what some people call white space, where you're doing non-value add items within your process. And they're the things you should try and cut out. Just a little aside there. Okay, so your pricing strategy, we went through that in the last seminar. Look at how you're pricing things, ensure that you're covering how you will recover the development costs if you need to. So if you're looking at commercial development, whether you're writing those development costs off, how are you going to cover future overheads, future development, ensuring that you're pricing within the market specs. So if you come up with a perfect solution, but it's 100 times more expensive than your competitors, you're going to have problems. And of course, our SWOT analysis. That, again, you'll use in writing up your final report at the end. So it's a very worthwhile document to use in the documenting of your project. Along with that, I've got a mental blank now. What is it? The lean canvas that you did earlier. Okay.
Sorry, Ian, just a quick note here. For those of you who've missed it, if you rewatch the second seminar, Ian went into a lot of detail about each of these individual points with a couple of more examples and some useful links. I would recommend taking a look at that seminar if you've missed it. And by the way, Ian, your camera is off,
Is it?
unless that's intentional.
Okay. Video's off. All right. I'll just. Sorry about that. I didn't know. Of course, because once I go out of the presentation, it automatically turns the camera off for some reason. Okay. So today we're going to have a look at some software development tools and answer these questions. Most of us have used the Arduino IDE. So why don't we use that or continue to use that when we're doing a commercial development? And there's very, very good reasons why we don't. So we'll also look at some of the other options that are out there and talk briefly about those. And I might get Sebastian to jump in on a few of those because he's using all the current stuff. I tend to be a little bit more hands-off. When I say a little bit more, I mean a lot more in the hardcore development stuff now. But Sebastian, of course, he's still doing that stuff. We'll have a look at some tools for custom PCBs, the design and production of these, some nice little shortcuts to get things done quickly and cheaply, and how you would look at doing things in a more commercial environment. And finally, we'll look at housings. How do we develop housings? Things to actually hold our device, make them look pretty. We've shown you some of our sticky tape models, but when we get to production, we really want something that looks the part. So this is my Oculus Quest hand controller. It's all nice and smooth. There's no rough bits on it. Lovely controls in the middle, and is a true marketable device. And that's really what we want to get to. But you'll find initially this might have been a old-fashioned joystick that was modified or something similar as they work through their prototypes. So we'll look at options for actually developing your final housing, and some of the things you really need to consider when you're designing these. Waterproofing quantity that you're making, durability, cost, how big it is, etc. I can give you the example of weatherproofing that was utterly disastrous. It was a development of Curtin. It was a large housing for some power electronics equipment, and they developed this nice housing. It was all weatherproof. It was done properly, but they ran the power cables directly out of the top of the cabinet. Now, it might be okay if you've got a weatherproof seal sitting around the cable, which they did, but over time, the moisture ran down the cable itself, condensated in that connector, and then dripped into the power electronics inside the cabinet. So a really simple solution for that would have been to have the cable coming in at the side and sloping down. So these are the little things that you have to think about from your design perspective. Right. Okay, so first question. Oh, we might even stir Hannes up a little bit with this one. The difference between computing people and engineers. We'll come into this a little bit later. So why wouldn't we use an Arduino IDE or the IDE that comes with your home development kit aimed at the hobbyist? They're simple. Generally, they've got lots of built-in libraries we can use, so it's nice and easy. You don't have to rewrite everything. Excuse me. It's very quick to change platforms. So if you look at the Arduino one, you just select which board you're using and bang, you're developing on a different board. Very easy, very simple. The issues start to become problematic because these IDEs, because they are developed to cover a very wide range of devices, the compiler behind them and the libraries they use tend to be extremely inefficient. They have to allow for all kinds of different hardware, different pinouts, different CPUs, different amounts of memory. So they are generic and therefore can become very inefficient. They also generally only work with existing prototype boards. So if you're developing your own board and you start to remove and add other components on those boards, these IDEs tend to start to fail. They may compile, but certain things won't work correctly. They won't work as expected. But of course, important thing is they are open source, which means they're free. But far more importantly, from a production cycle, they don't have any license fees. Some of the commercial products will say, yes, you can have this product, it's going to cost you $10,000, but every application that you produce with it, you have to pay a per item license fee to continue using it. So every device you ship will have a license fee attached to it. And that can become very expensive and very inconvenient. It also causes problems with reliance on a single vendor, which is always a bad thing to end up having. If they go out of business or they decide they don't like you and they're not going to support you anymore, you've got no alternative and they can just charge you what they feel like. Now, I said I'd have a little dig at Hannes here because we've had this discussion just a couple of days ago, actually. Software development has a couple of different philosophies to it. In computing, and feel free to interrupt because I can mute you, Hannes. It has two main philosophies, probably more. One is you develop for maintainability, readability of code, and this is where the computing people tend to concentrate. It's important for them in large-scale software developments to ensure that things can be modified, they can be updated, they can be fixed easily by a large team of programmers. So this is the kind of thing you would do on your IoT dashboard, the database system that sits behind it, the cloud development. You would want to have that ease of maintainability. Computer engineers tend to look at efficiency because we have devices which are very much based on limited resources. So whereas in the computing area, if you're writing something for your standard desktop and it takes 16 gig of RAM, well, that's fine. We'll just insist the machines have 16 gig of RAM. If it requires a quad-core CPU, no problem. We'll just make sure you've got a quad-core CPU. In our rice cooker that we're making an IoT device, we've got a 4-bit controller with 4K of memory, and that's it, and we can't change it. So anything we write for our embedded device may have extremely limited resources, and we have to be able to write very, very efficient code, even if it's at the expense of maintainability, readability. Our code, from an engineering perspective, has to be bulletproof because in many situations, such as the software running the embedded systems in a Airbus 330, we don't want any faults in that or have it fail in any way because that kills lots of people. If your word processor crashes, it just annoys one person. So reliability is far more important than maintainability and scalability for an engineering perspective. That's not strictly true across all fields, but it's a generalization that is, well, relatively general. Got any comments? Shoot me down in flames there. Hannes?
Well, one of the things that we do address a fair bit in computing is the trade-off in coding. So there's always a trade-off in time versus space. There are also trade-offs in manageability and, correctness effectively, because if you want to make sure that the program is correct, then that will incur an additional cost as opposed to, putting something together that develops very quickly. And then, of course, there's as Ian mentioned, the issue of developing large teams, which requires certain types of coding as well. I would argue that there are computing applications where efficiency is also very important, especially when you're starting to talk about GPU acceleration and all that sort of thing for very large projects. But I would agree that in general, we don't tend to look at the small scale, very efficient sort of scenarios that Ian is talking about. Although if you want to get that efficient, you probably should be looking at assembly language anyway, right?
Sorry, what was that last bit?
Just to tweak your nose a bit, shouldn't you be looking at assembly language or compiler?
We are in the very next slide. Yeah. Okay, so that was a little bit of an offshoot, but I think it's terribly important to understand that engineers and computer science people do approach a problem in a different manner. Quite often, there's an awful lot of commonality in it, but there is a preference, as I said, for maintainability, readability, and scalability in the computing side, and more of an efficiency, reliability in the engineering side, but they have a lot of similarities. So instead of using Arduino, the IDE, we can use something like this. Is this the IAR? No,
I think this is a code composer.
Yeah, this is Code Composer from Texas Instruments, and it's looking at a particular chipset, the MSP430, which is a mixed signal processor. And again, you can see it's similar in a way to the Arduino IDE. Over on this side, hopefully you can see my pointer, we've got our code, we've got the way the files are set up here, different, I actually don't know what those, but different parts of the structure over here. But the critical point is that this code ties directly into this hardware. So this is the internals of the chip, all right? And we can control single lines and what's happening with single signals throughout the silicon itself. This allows us to be very specific in what the processor is doing. Things like the Arduino IDE cannot do this. They treat everything as a black box. So the chip is a black box with little pins sticking out of it, and you've got no real control over what's happening internally. And you can't, because it's got to be flexible and work with other platforms. With this, we can actually look at our ports. Here's the RAM. I'm looking for the different timers. Yep, and there's your serial interface, and it gives you the lines, and you can actually watch what's happening with these. Another thing that engineers tend to do a lot more than the computing people is when they're looking at the efficiency of the code, you have something in a good IDE called a Hotspot Editor. And that shows you where your code is spending all of its time. It means that you don't have to try and create efficient code all the way through your program, particularly when parts are only ever used at startup, like your initialization. That doesn't need to be particularly efficient. But it does look at the areas where the code is executing the most amount of time. And instead of using a high-level language such as C or, God help us, Python in an embedded system, we can actually move down a level to the assembly language. Now, in case you're not familiar with assembly language, it is a representation of how the silicon and the gates and all of the logic in the CPU work. They all work on ones and zeros. Humans don't understand ones and zeros terribly well, so we give it mnemonics. And that's an example of it circled here. And it's basically setting our clock, which was over here, there we are, our basic system clock, to the frequency that we want this CPU to run at. And that's what I mean by detail. This CPU may be able to run at 10 megahertz, but it doesn't need to, and that consumes more power running at 10 megahertz. So we actually change the clock to suit the application and underclock it. So these represent particular values in octal. So this is setting our DC0 control, I would expect that means, to 0, and the other attributes there. So just looking for some more.
Yeah. Could I give a quick comment here? Yeah. So with these setups, as you can see, so these are the timer counter registers that we're modifying here. And one of the most common practices in kind of embedded system and IoT is the fact that when we write that firmware code, you're usually writing an infinite loop somewhere, and you're monitoring for an event to happen. So a very basic example of that, say you're monitoring the temperature of a system, and you want it so that if the temperature goes above a certain level, you would turn on a warning sign. Okay, so for that to happen, you have to interrupt your code. Now, if you bear with me just a quick second to take a look at the very low level of the computer architecture, the way we deal with the actual flow of the code, and if it's just a normal, and especially with an embedded system where you have a single CPU and the code is running in serial, what we have to do is we have to hold the current state of our program somewhere. So we put it in, we put it in the stack. Then we load a new instruction to our memory. We handle that instruction, and then after we're done with that, we have to then go back to the original state of the program when we were monitoring the environment, right? So this particular process, so where that event, which is the rise in temperature, would be interrupting our flow of the code. And because of this interrupt and the way we're handling this interrupt, it's such a low-level system resource thing where we have to have direct access to the memory and registers. That is why we would write this actual part where the code is handling the interrupt, and it's dealing with kind of holding the current state of the program, then putting the instructions for the new interrupt, which is turning on that warning light into our system. So it's such a low-level system resources thing, and we have to know what exact sequence of values are being stored in the memory. We go one level lower in abstraction level, and we write that part of the code in assembly. And one of the common practices is actually mixing C and assembly. And when we need that low-level memory control, memory management, we will write that part of the code in assembly. And most of these modern compilers like Code Composers or Code Composer or IAR, they allow you to mix C and assembly together. So if you do need to get access to low-level architecture of your embedded system and to write the most optimum way of handling an interrupt or handling something like a memory management type of a setup, that's where you would go to that assembly level, which of course we can't do with an Arduino. And one more thing, even if you compare the same very simple LED blinking code that would have been written in C, in something like Code Composer, or in Arduino, you can see even the size of your sketch, the size of the code that you will be putting on the board is going to be a lot different. Because with the Arduino one, you're also putting all of the resources that are there for setting up all of the other peripherals that you might not even be using, even if you're not enabling them, because as Ian said, the Arduino programmer has to facilitate lots of different types of boards, and old ones and new ones. So they still have to put all of those resources in there. So it's not the most optimum code. And actually, if you're limited by the size of your code and the amount of memory you have left for you, that would be a problem. And you can test that even you don't need to have access to these complex compilers, because you can still write a C code in Arduino IDE. It's just that you won't have access to all of these nice debugging tools and monitoring registers, but you can write the same C code in an Arduino IDE and then write the same code using their own language, wiring language, and including their built-in libraries. Then you can see the size of the sketch. That's going to be much difference comparing these two together.
Yeah. So memory footprint is another very important one. Power consumption is also another. Interestingly, I'll just quickly mention that Arduino have released Arduino Pro, which is actually aimed at the industrial market. So Sebastian's having a bit of a look at their new IDE for that, and it does have some of the debugging tools which are necessary in a production environment that the standard hobbyist IDE doesn't. So debugging tools are really important as well. Okay, moving on. So having the correct IDE is really important when you're going to a production level, and generally the free ones that you get aren't flexible enough or offer the range of options you need to produce reliable production type level code. Now, next step on, after writing the code and getting things working on your evaluation board is to start looking at developing the hardware in the most efficient manner. Sometimes this can be just an off-the-shelf board that you put into a case and use, particularly when you're just working on a software level system that can work on existing Raspberry Pis or other small single board computers. However, in a lot of cases, you want to be able to produce a custom PCB to reduce the footprint, to make it fit a particular device. See if I can show you these. So I have one of my favorite examples. This is by a local West Australian company, and I may have actually shown them before. It's never very good, but this is a noise cancelling hearing aid type earbud. So it does all the things your normal earbud does. Did I just break up there? Yeah, it does all the things a normal earbud does, but also acts as a hearing aid, hearing protection, and several other features. As you can imagine, that's not something you could develop on a standard evaluation board. So you want to take it from an evaluation board through to something that's going to fit the application that you're actually developing. So on the left here, we can see our famous sticky tape prototype. Everything in there is on standard off-the-shelf boards. So I think at the top we have our IMU sitting there, which again, just bought from Adafruit or one of those. We have a RF module here. Could be a Bluetooth, but I think it's just our standard RF. Underneath that, we have the Arduino board itself, a little prototyping board to hold the switches and power and on-off and that sort of thing, and the battery sitting underneath. So this is made completely from off-the-shelf bits of equipment. We then have a case that we made 3D printed, which I'll talk about cases at the end, that holds this, and it works perfectly well to prove the concept. However, if you were going to go out and spend several $100s on an IoT device, would you pay several $100s for something like this? No. The other thing is, where we've got all these wires connecting things up, they're a point of failure. So you want to avoid having wires that can vibrate, break off, and decrease reliability. So these devices, although they worked, were, how would we put it, somewhat unreliable. We were continually having them shipped back from hospitals. These are a measurement unit for, yes, it was the cerebral palsy trials. And they would come back to us on a regular basis for repair. So not good for a production environment. What we really want to get to is something along the lines of these two. Just out of interest, this is a hardware text-to-speech engine for use by people with vision impairment. You throw in text on the RS-232 or the USB, and it then turns it into synthesized speech. This is an ultrasonic guide for again, a blind person, and it buzzes or vibrates relative to the distance you are away. But as you can see, apart from the battery connection here, there's no loose wires. It's a neat sort of shape so we can fit it into a housing. This one is specifically shaped so that it can be used like a torch, so it's quite small, and can be pointed at the path of the user, and they have much higher reliability. I will talk a little bit more about this one because when we manufactured the PCBs, we had a bit of an issue. So we want to go from this sticky tape over to something that is reliable, can be packaged correctly, so that it's suitable for sale to our users. So first step in getting that, we've got to design the PCB. Now there's a whole bunch of programs out there that will help you do this. From the hobbyist perspective, things like Fritzing are really good. They allow you to do a board layout like this and test it out in simulation. You not only get the board layout that you can develop on, again, it's limited to things like Arduino. You get the schematic, which shows how the devices are logically laid out and how they're physically connected. And from there, it will give us a PCB. It can generate these automatically, and However, quite often when you automatically generate the PCB from this schematic, it won't put the tracks in the right or optimal places. Generally, we don't have to worry too much about track placement in simplistic type projects, but as we get into more complex projects, then we need to be very careful about where we place tracks, where we have earth planes and earth lines, where we have power leading onto the board and we need capacitors to store an extra charge on the power lines. Probably a little bit more detail than we need to get into here. So if you're interested, we can talk about it separately. But there is a lot of aspects that you need to start looking at in customizing a PCB. All right, so fritzing's a really good one to use. It can give you some idea of the physical layout of the board, and you can produce a PCB and then generate the order for the board as well, which I think I'll show you a little bit later on, but we can actually do that. In actual fact, Sebastian, while we're waiting, or while you're waiting, you want to just fire up one of the fritzings or the ones that link directly to PCB manufacturer. Have you got Eagle or fritzing on your machine?
I don't have them on the machine, but we can go to PCBWay and show how the ordering process would look like what sort of settings they'll have.
Have a quick look at that while I go on to the next level. Again, one of the major points with things like fritzing is it is free. There's no license fees. I think they make their money by getting a kickback from this fabricate button. So when you hit the fabricate, you order the PCBs from the manufacturer and fritzing get a bit of money from it. So they probably have a plan like that. It's definitely worth a play with. It's not a bad little program. Next step up from that would be something like Eagle. Now, remember, these are only examples. There are lots of them out there that you can choose from. Eagle has several levels, so you can get a limited version for hobbyists. That allows you to have two schematic sheets, 2 layers on the PCB, so you can have a dual-layered PCB. I think fritzing only allows you a dual-sided PCB, and that's it, and a limited area. Again, it's worth a look. It's scalable, and very importantly, it's cross-platform, so you can run this on Linux, Windows, and Mac. So it's not tied to a particular platform. Advantage of something like Eagle is that you can actually scale it up. So you get your limited hobbyist version. As you want to advance further and do larger PCBs or more layers on the PCB, you can start paying for the license and get those attributes in there. So that will take something from a schematic. So you actually enter the schematic in and produce a PCB from there. Again, it will automatically place everything for you, but it mostly doesn't do it in an optimal manner, particularly when you start to get into more complex boards with high frequency signals and greater power requirements. So again, a really worthwhile one to look at. And then we get to the real ones. Now, these real ones generally don't have a free version that is usable. They allow us to do a huge amount of testing, playing around with. They can do things like heat maps, so we can see where the power consumption is being used to adjust the cooling on the boards. It does frequency interference. You can have multiple layer boards, so 16 layers per side, which you need when you start to get high density pinouts on the chips. And Altium actually allows you to do a 3D model of the PCB, so you can see how it's going to fit in the case. It also allows you to do a 3D model of the case. So very complex package. The training for it for skilled PCB designers, the training to go to Altium is around 10 days long, 10 days full time. So if you already know how to develop PCBs, it takes you 10 days of full-time training to learn how to use Altium. So very, very complex. It's also a little bit pricey. The starting price for a single installation of this package is over 10,000 Australian dollars. So not cheap at all, but it'll do everything you ever need to do in a PCB manufacturer. All right, so they're the sort of ranges you get. You can go all the way from free right up to incredibly expensive. In fact, Eagle, when you get to the Autodesk level, is also very expensive as well. Altium, again, wonderful little Australian company. They started in Tasmania, which is that little island off the southeast corner of Australia. Now a major international company and a major supplier of PCB development software globally. All right, let's get to the next one. All right, so once we've got our PCB drawings done, we need to get that manufactured. And I've got a picture here of one of the manufacturer's sites, really nice, simple, easy to use, and very, very cheap. My phone's good. Excuse me. All right. A link to online stores. You'll probably find there are local PCB manufacturers where you are, and that can be good. They tend to be a little bit more expensive than the online manufacturers. They deal in very large bulk runs, so don't have the same sort of setup costs. Usually in countries where labour cost is very low, mostly China at the moment, but that'll probably move as China advances. But they are very simple to use. They require something called a Gerber file. And you might be wondering what that funny little blue machine up the top here is. That is a Gerber sign writing machine. I used to actually work on those, and I actually developed one of my own, which we sold around Australia back in the mid-80s. And because this works on an XY cutting out of the vinyl on a sheet, it's the same way as we cut tracks out. So they were the very first PCB manufacturing machines, very expensive machines too. So you require these Gerber files, which allow you to create the cutout tracks on a PCB. Quite often, particularly in early prototype stage, you'll want to use one of the online stores, but you've got to be very, very careful about them. What happens if something goes wrong? You end up with a whole bunch of PCBs, online store, they're not going to take returns. Bad luck, your problem, you've got to do it again. You can also order them fully assembled, which can be very, very cheap. So they will place all the components on and solder them for you. But, and going back to my example, this one here, when we had it, sorry, yeah, it was this one here. This one here, when we had it fully manufactured in China, we supplied them with these custom chips that we had. They sent them out, and they'd just gone and replaced the crystal, this little tin here, with one that they had, even though we had specified a low height. And what that meant is we couldn't actually fit this PCB in the case. They'd done it to reduce their costs, but it ends up costing us a very large amount, having to remove this crystal, throw it away, and replace it with the low height crystal. Once we did that, we actually tested them, and we had about a 30% failure rate. So a third of the boards weren't manufactured correctly. On the plus side, it cost us very little, and we could afford to throw out a third of the boards, but it is very wasteful. All right, so yes, you can get them fully assembled. That can be very cheap, but you quite often will have very iffy quality assurance on the end product. That usually doesn't matter too much for your first run. So you'll do a first run nice and cheap, do your version 1, use it for your field tests, pick up where the problems are, and then go to a high quality manufacturer at a later date. And if we need anything high quality manufactured, we will get it done locally. So we can deal with the company directly. If there is a problem, we can fix it quickly. But they do cost a significant amount more. Right, so here's an extension of the software that you use. You'll see you've got lots of options here, and they tend to start to increase the price as you add in extra bits and pieces, like the number of layers. That's 14 layers per side. So you can have 28 layers of tracks on top of each other. PCB thickness, track spacing, where's an important one? There we go. The copper base that you're using, that's very important. It's a significant factor to look when you're developing your power consumption. Are your tracks big enough, wide enough, and thick enough to handle the current you're drawing and dissipate the heat? Another thing you want to be careful of is if you're going for something like a 2-layer board and you use your signal tracks on both sides of the board, you can get a lot of interference. So where you've got signals clocking away at a higher frequency, that signal is induced into other tracks, creating noise and faults on the board. So quite often what you want to do is you will increase the number of layers you have, but use one of them as an earth layer to shield the signals from each other. If we can, Savash, we'll go off to PCB GoGo. It's a nice, easy one to go to.
Sure, I have a couple of them open here.
Okay, good. We'll get to that in a second. Let's just get through the rest, which is housings, the last and final step in producing your device. We need to put it in something. We can't send out unencapsulated PCBs. They get dirty, they break, and they don't look very good. So again, there's many levels you can go through on quality, price, availability, etc. Our first one to look at would be the infamous Jiffy box. And these you buy from any electronics store. They're standard shapes. They are very, very cheap, relatively, in low numbers, but they aren't particularly fancy to look at. So if you're doing very low runs or your device is hidden, sitting inside some other device or perhaps in a cupboard, Jiffy boxes are fine. Use them. You can get them in all kinds of weatherproofing. As I said, many different sizes and shapes. So they are suitable for low run, non-user space applications. So when people aren't looking at them, and worth a look at, particularly in the prototype stage. The next step along would be to 3D print things. Now, 3D printing is a wonderful, wonderful tool nowadays, but there are issues with 3D prints. The first one is you'd only ever use it in very low runs. So producing your first prototype casings to see if it actually holds the board, to see if it's a useful design for the device itself. Main issues with it is that it's incredibly slow. To produce a box like this one up here, you're probably looking around 3 to 4 hours as a minimum to print each one. So it's not viable for any large production run. It's very, very cheap though. The material we use in our 3D printing costs around $30 a kilo. And you get a lot of material, a lot of boxes and housings out of a kilo of plastic. However, you do have a fairly high wastage. When you're printing things, quite often they'll go wrong. It'll slip off the base. Things will warp. So you'll end up throwing out an awful lot of plastic, which again is not good, not just for the cost, but for the environmental expense of all this plastic being wasted. And generally the quality isn't all that good. If you look closely at that box at the top, you can see each of the lines that's been printed. You get little lumps of plastic around it. That pattern on top is from where it sits on the bed to be printed. You can do a lot of hand finishing to clean this up a bit, but again, that adds a lot of time. And they really are only good for prototyping and initial small run cases. One of the other issues is some of the materials can be a bit iffy. For instance, ABS is fairly rugged, reliable, long lasting. PLA, which is a modified form of cornstarch, is good in that it eventually with some treatment can be biodegradable, but it's a plastic that tends to become very brittle over time and won't last very long. Nylons and other materials that you can 3D print with tend to get expensive. Okay, the next one along is rapid prototyping. This is a rapid prototyping case. These are made with sort of temporary molds to form things. Generally not for production because they don't have the physical strength, but they use them for mock-ups. At one point I had a picture of a complete rapid prototyping motorcycle that was made with every single part that was in the motorbike, and of course didn't run, but it showed how everything fits together, and they used it in setting up the production line. So they would take all of these prototype parts and run it down the assembly line to see how they could actually assemble the motorbike. Rapid prototyping is also very good for producing samples, so non-working samples. Vacuum casting is another method, and that is relatively cheap. It uses thermoplastics. They're heated. They're pulled down over a mold and a vacuum draws the material in. You see this a lot in things like bottles. They're blow formed. Pots that are used for in gardening. They can be vacuum formed, but the quality again is not great. When you get to a real production run, you really want to go to something like injection molding. Injection molding is in this frame here, and we can see we have a mold that has a hole in it, and plastic is injected, or the material is injected at high pressure, in this case producing a little chess piece. And that means you can produce things in extremely large quantity at a very, very low cost. However, the downside of this is an injection mold die. I used to actually have a factory that made these as well. It's very different things. Did a lot in plastics, but anyway. And the normal cost in the up to fairly recent times of producing one of these, you couldn't produce anything below around $40,000, $40,000 to $60,000 Australian. There are cheaper ways of doing things now, particularly with CNC machining and that sort of thing, but the price is still extremely high. So you've got a setup cost of, say, $100,000 before you produce a single item. Once you've got that set up, then you can produce things for tenths of a cent for very, very low cost. But to recoup that 100,000 initial investment, you have to be producing a lot of devices. Nowadays, you could probably get an injection mold setup done for possibly around $10,000, but it really wouldn't be much less than that. So if you're producing something along the lines of consumer devices, then injection molding is the way to go. But as I said, very, very high setup costs. All right, that's about it. We'll just cover this last bit. I think we did this last week, so I won't go through it again. And I will now hand over to Sabash, who's going to take us through a couple of things. Hopefully, I'll stop sharing.
Okay, just share my. Where is it? Oh, there we go. So yeah, just bring this window. That should be fine. So I have a couple of these PCB manufacturing websites open here. So Adrian was showing some of these, some of the options that they can offer for you. So the type of board, where you have single panel, custom panels, the different number of layers that you end up producing for the board. And typically, when you go above 2 layers, they tend to get more expensive, because most of the free available software allows you to go up to 2 layer. Like I think a student version of Eagle is a good example that allows you to go up to two layers, and if you add layers to it, because it will get more complex to manufacture, the price is going to kind of exponentially go up as well. So you have options like the size of the board, the type of material that you want to use, and some of these manufacturers, so this one is PCBWay, they also offer assembly, and with assembly of the device, they have options where they do the full assembly themselves and they purchase the parts as well. And then they have options where you provide some of the parts and then they assemble it for you, and they do SMD stencils and things like that. PCBWay, another one, just to give you guys a couple of examples of websites that you can check out. This one is JLC PCB, very similar, and this is the Gerber file that Ian was talking about. I don't know, it's Gerber. Basically, this is kind of a unified format of your overall design file that after you've designed the PCB, you can save it as a Gerber file, post it here, and that the Gerber file would typically have both your full design and your component list in there. And they will be able to kind of produce it for you. Some of them give you kind of the option of different colors for the boards and that type of stuff. Another one that we could check out, this one is PCB GoGo. This is the one that was in the slides. Fairly similar to PCBWay in terms of options that they provide. So again, PCB assembly. Some of the companies, by of course charging you, they can charge you to do some testing for you. So they offer a bit of guarantee on the ones that do go under testing, and even some of them test your circuit design as well to make sure some of the interferences, as Ian was mentioning. So if you have kind of two signal layers close to each other and they suspect that there might be an interference from the signal layers, they'd be able to kind of detect that and give you some options for modifying it. And of course, all of these stuff would add to the cost. The cheapest way would be just to manufacture the PCB yourself and start kind of soldering the components yourself. But if the parts are common enough, the assembly, ordering them assembled wouldn't add too much to the cost. And of course, well, we have a chip shortage these days, so things get a bit more interesting. So I would say if you're looking into manufacturing, that's probably something you have to keep in mind as well. So depending on the chip shortage, if you're looking for a specific controller or for a specific type of SMD mounted part or component, it would be worth it to see how readily available that part is at the moment, if you're at the point where you're close to going to production for your device. So it might be that there might be a better chip that you can use for your device, but if it's part of the shortage, so that might be something worth considering to maybe change your design slightly, because then you don't want to have a very good design that you can manufacture, like the situation I guess Microsoft and Sony are having with their new generation of consoles, where you have these devices, but they can't manufacture them fast enough. And they're already thinking of redesigning just less than a year into kind of their release cycle. One more thing, I did post this link in the chat. This is a tutorial directly from Fritzing that takes you through how you go from a schematic design in Fritzing and then get a PCB for it and order it for manufacturing. And one of the, I guess, typical ways that you would start with a PCB design is you might start from a schematic point of view, and then have the program that you're using for PCB design auto route. Then you go and fix those routes. Make sure all of the signals and all of the power lines and all of the ground planes are separate enough with each other, and we do refinements on top of that. So unless it's a very complex board, you typically don't start from without any connections and start connecting one by one. Usually start with auto route, and then you do refinements on it. And of course, the more expensive and the more robust the actual IDE for PCB design is, the better the auto routing feature of it would be. I think that covers a couple of examples, and that should give you a couple of ways to look at these websites. So just to review, we had PCBWay. This one is a JLC PCB and PCB Go. All three are Chinese companies, so they can.
I just look at the pricing as well.
Yeah.
If you go back to that PCB GoGo, what have you got? You've asked for it for 3 to 4 days.
Yeah.
How many did you order? How big is it?
I think this one I ordered like 15. But I think the size I went pretty overboard. So let's do this one. So multi-level. That's
an awfully big PCB.
Let's do. Oh, that's the minimum they do for this type. Oh, that's because that's the SMD. That's the SMD. Yeah. So let's do like 2 layers. I don't know, like millimeters, like.
Yeah. So
10 to 10.
75. That's tiny. That's you're looking at
Yeah. So let's do
That's just a,
something like that.
yeah, that's fine. Yeah.
Like,
Order 10 of them. It's just a nice small run.
so 2 layers, material, that, all of the, leave most of
Yeah,
this
leave everything else pretty standard. So just a quick prototype.
Yeah.
Yeah.
Calculate. So
There you go.
yeah, 45
Shipping
for
is
how many?
almost more than the cost of the boards.
Yeah.
So you're looking at $26,
Yeah.
$2.60 per board, small run,
Hmm.
very, very cheap. And that's one of the more reputable ones.
Hmm.
Is that a US company or?
I'm pretty sure they're in China.
Yeah.
Yeah. PCB Way. Check.
I just did this online 3D print quote. So when you're done, I'll jump back to
Sure.
the sharing my screen.
I'll just find the stop sharing. There you go. Okay, should be able to share.
Okay. Just as an example, share content. And back we go. Okay, there we go. So this is you can see this, the PCB, sorry, the casing. All I did here is just upload a STL that I had, which is the 3D printing file. It's a fairly large one. It's 133 by 165. So it's quite a lot of material. It's a one-off using the standard printing. So I can get that done for $126 in PLA or carbon fiber, $1,000 in carbon fiber, polycarbonate, which is nice and hard. Yeah, I'd rather have the carbon fiber. PVA, which is a type of glue. So most people will use PLA or ABS for this, but this is just an example of using FDM, which is the standard filament ones that they all layers down. And as you can see, without having to buy a 3D printer, I can get a fairly large piece produced as a prototype for quite a reasonable cost. Well, we can choose all different colors too. So we do it in yellow, still the same price. And it's a 3-day service. So that was just an example of you can get cases 3D printed at a reasonable sort of cost online, sent out to you. This is just a Melbourne-based company. Could probably find a lot cheaper around, but online is a wonderful thing. All right, has anyone got questions, something they want to raise? We're just out of time. How about that? I can hang around for another 10 or 15 if people want to ask things. I'm not sure about you, Sebash.
I have a couple of minutes before my next meeting. Students aren't hovering yet, so it should be fine.
Jean-Luc.
Please. Okay, you mentioned Code Composer, Arduino Pro. Have you heard about MCU Expresso from the company NXP?
Expresso.
MCU Expresso.
NXP I'll from somewhere.
Yeah. Interesting. Do they provide stuff for STM boards?
Yeah. I haven't used it.
No, I haven't
Okay,
used
so
it.
I think they are focusing on their own products mainly.
Yeah, I'm looking at their website. It does look like they do offer kind of disassembly windows and debugging tools, which is good. Yeah.
But I think you'll find most of the large chip manufacturers would offer their own. I just had a really quick search and I found Fortis Pro, which is the Intel-based one.
Okay.
So they will deal with the any Intel designs. So you'll find that most chip manufacturers would have some form of PCB design because it'll have all their models in there. And that, again, is used in the higher level design where you're actually doing the simulation of the hardware at the same time so that you can check your signal timing, full testing to make sure your design is correct. So when you're getting to those complex designs, this is why it takes 4 or 5 years to become a computer engineer. There's a lot of things to look at, particularly with the RF, the interference, power supply, because every time, the reason I mentioned the capacitor on the power lines, they're really important. So between where you feed the power in to the board and it reaching the chips, you normally put a capacitor in there which acts as a storage, because when a CMOS chip switches, so it goes from 0 level to the 1 level, that change is when the current is drawn. All right? And the faster you clock things, the more current is drawn. Quite often you'll find that the power supply can't cope with that sudden surge in requirements. So you put a capacitor on there to actually supply an extra charge during switching. And that stops this ripple coming through on the power lines. So there's all kinds of little things like that you've got to look at, and you need a simulator to actually ensure that your values, your track spacings, where you put your tracks, are in the right position.
Okay. Thank you.
Sorry, Jean-Luc, while I've got you here, did you submit your Canvanizer? Did you submit your Canvanizer?
I have a little issue with it because I realized the 4th of May. Oops, the course started some time ago.
That's okay. So if you could, because I think you might not be able to submit again, but so you can email the link. You can email the link directly to me, and
Okay.
I'll go ahead and mark that for you, because the first one was peer assessed. So
Yep.
I think with the edX, if it goes past the submission date,
You can't peer assess, yeah.
No, it's no. I want to. Well, it's 10%. I want to succeed the others.
Sure.
So
So
okay.
I'd be interested to see, because I just saw your video. I'd be interested to see your Canvanizer as well. So once you have it, just send it directly to us. I'll take a look.
Yeah, just for curiosity. Well, thank you very much.
No worries.
I was very happy to have information about Fritzling and about the creation of a PCB, and I realized that creation of a PCB requires some skills. They can be advanced if your PCB is rather complex. Cadence is a company providing. They provide. Yes, they provide very good design tools.
Yeah, I've used their tools to do something similar to PCB design, but VLSI design, so low-level silicon layer design for internal IC circuitry. They're interesting. They have very interesting tools, and the design on that low level gets very fun, because you have lots of considerations when you're drawing your layers and all of the capacitance effects that will happen just by making a simple connection.
Yeah.
Okay.
I'll just quickly share this one. Now that you've mentioned VHDL, just got one up. Just an image grabbed off the web, so you can.
Students are.
Come on, where are we? Share. There we go. You want to run through a little bit on that? We can see that we're setting all the digital values for the actual silicon. It's written in a C-like language. VHDL stands for Very Large Scale Integration Hardware Description Language. So it's an acronym of acronyms. And it allows us to actually lay out the silicon how we want it for a particular device. And you'd use this in a case where you're having possibly very large production runs, and you develop your own silicon produced by a third party normally, well, always, except for companies the size of Intel, to produce a chip which does everything that you need it to do. So you can end up with almost a single chip solution to your issue. And you can see some of the language in here, and it does look very C-like, but it's describing the hardware.
Yeah, VHDL is very interesting because it was based on a programming language. That's why it looks like a programming language. But as Ian said, you're just describing the hardware connections. So it's not a code that actually gets compiled. We call it the code gets synthesized, the VHDL code. But yeah, it's an interesting thing.
It is. It's a fun thing to play with. It was very early development when I was doing my undergrad degree. But it was absolutely intriguing to play with. One of my favorite units when I went through uni.
And I can quickly share something as well. This thing.
I'll stop sharing.
Sure. And I'll head off after this. So this is what I did for my master's. This is a VLSI design of a very simple digital signal correlator. So these little blocks over here, they were all individual NAND gates. So I started by building a MOSFET, then connecting those MOSFETs to create a NAND gate, then using those NAND gates to create two large registers. Then this was just basically a signal correlator, but I was investigating the complexity of that on an IC level. So then I have this adder system. So this is an XOR system that I would XOR the bits. So add the bits together, XOR the results, and then store them in the final register to get their correlation. So it gets interesting on that level when you're designing. So I think this is my one of the full adders I ended up designing by the individual MOSFETs I had.
Yeah, and if you sent that off to one of the manufacturers, that actually just produces a chip.
Yeah.
So you will get a chip that performs that full function, custom designed to do exactly what you want it.
Yeah, and I think I ended up also implementing that on an FPGA so I can show the functionality of it. So from a block diagram point of view, it looks like something like this. But yeah.
And that's how complex things can get.
Yeah. All right, so I'm gonna head off to a couple of students.
Anyone else got anything? I'll be here. I'll be heading in fairly soon.
Okay, sure. I'll see you later, Ian.
Okay, see ya. Okay, any questions? I'll stop the recording now, actually.